This meeting is being recorded.
Today in class, couple of things for us to go over, a lot of things for us to go over. Starting here on the class webpage here, I've posted this new topic 2 folder down here. If we click on that, that will take us to a bunch of stuff here. This notes1.pdf is the printout that I have up here. This notes1.pdf is the printout that I have up here. So it's the electronic version. There's also a physical copy of a textbook that we'll be using for the next month to 7 or 8 weeks, a couple weeks in the class. If you would like a physical copy, it's up there. Those physical copies are for you to keep, do whatever you would like for whatever your reason you want. They are your books. They are not on loan from me. You can do whatever you want with them. If you would like at the end of the semester to give it back to me so I can pass it on to somebody else, you're welcome to do so. But if you would like to burn it, then you're welcome to do that as well. These are your books to do whatever you want with. If you would prefer an electronic version of the book, you can click this link right here, and that will get you an electronic version of the textbook. For next week, so we're going to start going over the textbook material this week in class. For next week, I would definitely recommend that you read the first chapter. I will be assuming that everybody has familiarized yourself enough with the book contents from a first overview of reading that chapter. But I also realize that the midterms next week, we're having the in-person midterms that you have scheduled or should schedule if you haven't yet on the Google Sheet for the next week at different times. And very understandable if that takes priority over doing reading, which is not going to be explicitly graded in some way. But still recommend that you don't just put off the stuff that we'll be covering in class today and next week. Still try to keep up with it because you will be evaluated on it in another oral exam at some point. And it'll be very easy to fall behind. There's a lot of technical stuff that's going on in this class. And so try not to fall behind this week. I have some notes here about the midterm. So another policy has changed. I've said things sort of like this out loud, but I'll make this an explicit policy at this point. If your midterm grade is greater than either of your previous quiz grades, then I will replace those quiz grades with the midterm grade. And that can apply to not just one of those quizzes, but both of those quizzes. So again, my sort of overall philosophy of grading is that if you can demonstrate to me that you have acquired the knowledge and the skills for this class, it doesn't matter to me whether you had a bad day on a particular quiz or even on this upcoming oral exam. If you have a bad day on that, there will be chances for you to make up those points as well. My hope is that you will, at some point, though, master that material. And once you have that material mastered, I will award the appropriate points for you. So if for whatever reason you're not satisfied with your current grade because of those, you didn't feel like you did well on those previous quizzes, this is your chance, this midterm is your chance to make that up. Another quick recalling thing about this midterm that you are studying right now for the midterm to get a grade in this class, but maybe even more importantly for your future careers. All the studying you do for this upcoming midterm is things that you will be expected to know and be able to present in an oral interview if you go on to try to do a technical interview somewhere. And the first day in class, I talked about how machine learning engineers, so this is the sort of job title that this class is preparing you for, that the oral exam that you'll be having next week is that oral exam is designed to be an interview like the interview that a machine learning engineer would be getting. And machine learning engineers are sort of like the most elite, the top tier of people in the software engineering or data science world. On the the actual README file for this class, the main syllabus file at the beginning. Very first day of class, we walked through all of these different links about what people get paid, and we saw that the machine learning engineer job title down here got paid significantly more than all of these other job titles. It's something around like $250,000 a year. It's again not necessarily a beginner entry-level salary into that field, but a typical salary for somebody who is mid-career. But that's if the material is not intrinsically motivating you enough to study for it, hopefully those extrinsic motivations are helpful for that. Another announcement thing about the PageRank coding assignment. I've decided to move the deadline from this coming Sunday to next Sunday, so you have more time to work on it. I still recommend very strongly that you complete it by this Sunday, or in particular that you complete it before you have your oral exam with me, because the purpose of this assignment, the reason the assignment is structured the way it is, and the particular tasks that you have to do on the assignment, the reason they are what they are is because they will help you study for the assignment. So like last time in class on Monday, we spent a long time talking about how the alpha hyperparameter, how it relates to various different properties of the algorithm. And there's even more, there's essentially an infinite number of ways of explaining those different things that you're not going to internalize all of them, but you want to internalize as many as you can. And the assignment has tasks in it that will help you internalize that thing in particular, the alpha hyperparameter, and many other concepts. So I recommend completing the PageRank coding assignment before your exam. But if for whatever reason you can't, you have until next Sunday, 29 September to complete it. Last sort of announcement-ish thing is that, again, so the office hours moved from Thursday to Friday this week, 9 to 11. I am open to having a special dedicated office hours either at that time or a different time that is just dedicated to midterm preparation and nothing else. In order to get that though, specifically in order to get it for the normal office hours time, I will need somebody to post a GitHub issue and have at least 3 other students confirm that they would attend at that time, and then I will block that off. Nobody from other classes or anything will come to that office hours. We'll only talk about midterm prep sort of issues. If you want an additional time beyond that, then I don't have a specific set of requirements, but post it to GitHub, and I will consider, depending on my availability and your all's availability and my sense of how much effort you all are putting in, whether that is something that we can do or not. Any questions about administrative things? Yes, Ambika. So the question is, so I'll just re-explain what's going on here. This specific requirement, if this thing is met right here, then so one person posts a GitHub issue and 3 other people confirm that they will attend, then I will block off this current Friday's office hours from 9 to 11 and make it only about midterm prep. I am open to additionally having extra special office hours at a different time that is not the normal regular scheduled office hours time. Whether I do that or not, I don't have a specific guideline on what needs to be fulfilled for that, but you will need to post a GitHub issue suggesting that, and there needs to be some sense on my part that you all are putting in sufficient effort on your end for me to justify putting that extra effort in on my end to do that. Yeah, but this requirement is specifically just for this office hours time block. Other questions about things administratively? Okay, everyone's excited to do an oral midterm exam? I'm guessing for probably, maybe not quite everybody, but probably the vast majority of you, this is the first time that you've had an oral exam before. Yeah, language things, often you talk in language, so you have to have oral exams. Besides just language though, you talk in every field, like machine learning, you have to do interviews. When you actually have a job, you actually have to talk to your other coworkers about things. And so the ability to talk about these technical subjects is, I think, a very important skill. And so I think these oral exams are particularly good for you all, even if they feel particularly nerve-wracking. But besides the fact that they're good for you all, like skill-wise, again, I think they're also good for you all grade-wise, because if you say something that would get you 0 points on a in-person or a paper sort of test, I can ask you to clarify what you mean and help you get as many of those points back as possible. So even if the oral exam nature feels extra intimidating to you all, the grades tend to be better in the oral exam because of that ability for me to find ways to help you get more points. That said, you do have to study a lot for this exam. It will be a hard exam. Okay. Let's see. Maybe before we go on to new technical things, does anybody have questions about PageRank stuff? We can do some couple minutes of PageRank stuff here before going on to new stuff if you all would like. And I think I was a little bit distracted here before class, so I have to bring up my PageRank notes and my other notes, but I'm going to go to the, where am I, what am I doing? I need to open up the PageRank notes project, CMC. Let's go to the notes 3 over here. Maybe since nobody's jumping up and down with things that you are super excited to talk about, I'll mention that today I accepted a pull request for a typo that was fixed on the PageRank's 3 notes right here. I won't always talk about in class the different typos that happen and that I accept as a pull request to fix. That if you all are signed up for the to be watching the class, getting the emails about the issues, then you got the email that I accepted this pull request and the change. But it's a very minor change right here. Just that in equation 3 right here, where I have this x times a matrix, this vector times a matrix, there was supposed to be a transpose, that these things right here, both these x not qk things should have a transpose inside of them. And that's just the typo fix. That's required to make the dimensions line up. Question, Angelina. Packet number 3, problem number 3. So this thing that I'm looking at right here. The part 3 of that. So the question is, there's a lot of text here, a lot of fancy math equations, a couple of scary Greek letters. Let's talk about it. Let's go over it. The first thing to remember on any of these algorithms, whether it's the PageRank algorithm or whether it's the power method with the sparse vector, the power method with the dense vector, or this exponentially accelerated power method, is that the way that we know whether we're done with our algorithm or not is that we're measuring some quantity and whether it is like a good enough quantity. So here, this quantity that we are measuring is this yk minus 1. I think the notation from the packet 2 on the standard PageRank method uses the letter x for the thing that we are measuring, but it's still somehow like the difference between 2 values that we're iterating over. This k up here is somehow the number of iterations that we've done, and the y's over here, in this case, are y is the name of the variable that we're iterating over. And this difference between 2 things is called the residual. And oftentimes you will see people just talk about the residual, not provide any formulas, and you're expected to know that that's the difference between the 2 last 2 iterations of whatever algorithm you're using. And sometimes people will just provide the formulas like this. But in general, we run these iterative algorithms to some number of steps, which we don't know in advance, but we run it until our algorithm is good enough as measured by this epsilon. So this Greek letter here is epsilon. A number of you have in office hours or different times talking to me, like mention different Greek letters or use the, you'll write the right Greek letter, but you'll say it differently, say the wrong name of the Greek letter. That is something that will totally throw people off in like a technical interview and make it seem like you don't know what you're talking about if you don't even know the names of the Greek letters. Makes it seem like you just don't do a lot of mathematics. So this is one of the things, like the basic things to make sure that you definitely get right on the oral exam is know the names of the Greek letters that you are using. So here, this E is epsilon. The way that I write out the epsilon to make it look different than an E, and this is the standard way that people actually write it versus how it's typeset on a computer, is something squiggly like that. That is the epsilon, and that is our measure of how good we are. We want to keep going until our residual is smaller than this epsilon. And everything that I've said so far is true about this EAPM, this exponentially accelerated power method, and it's also true of the other two versions of the power method that we've talked about. The thing that's different here about the exponentially accelerated power method is that it is exponentially accelerated. And one way that this exponential acceleration comes in is in this formula right here, where we have, instead of alpha to the k on our bound over here on the size of the residual, we have alpha to the 2 to the k. So this bound here is exponentially better. Exponentially better than the standard power method bound, than the power method, PM for power method. So the question is, how many iterations do we have to do in order to achieve a particular target value, epsilon? Well, we need our residual here to be smaller than epsilon. Here's our bound on the residual. So if we have that alpha to the 2 to the k, if we say that that is equal to epsilon, then epsilon will be a upper bound on our residual over here. And I'm just going to write the word residual. The residual, so this big equation right here inside the L2 norm, that's less than or equal to alpha to the 2 to the k by this theorem, which I have stated without proof. And we set that equal to our target accuracy value. And we will solve for k now to get the total number of iterations that we'll need. In order to solve for k here, I can first take the log of both sides. So I'll do, that looks like 2 to the k log alpha equals the log of epsilon. And then 2 to the k over here stays on the left-hand side. I'll divide both sides by log alpha. 2 to the k equals log epsilon divided by the log of alpha. And I'm solving for k, so now I need to take one more logarithm. In this case, I'll make it a base 2 logarithm. Well, I guess the base doesn't even matter, so I'll just keep without specifying the base and just say logarithm and say k log 2 equals the log of all of the stuff on the right-hand side over here, log epsilon divided by log alpha. And then if I put this into the asymptotic notation, the constants will drop out and get k equals O. In this case, we could also say theta, but I'll just go with O because it is also true. O of log epsilon over log alpha, like this. Last time in class, I gave you the final answer to this problem, and I said that that final answer was this big expression. So it's the answer to part 4 right here. What is the overall runtime here? And the overall runtime is going to be cubic in cubed times this big long expression right here, log epsilon over log alpha, like this. And that's our overall runtime. All the fancy log stuff comes from the total number of iterations that we're doing. And this in cube stuff right here, that comes from the fact that there is a dense matrix multiplication that we have to perform. A dense, a matrix times matrix multiplication. And so it is also the case that I could reduce this this upper bound by, instead of n cubed, using the naive matrix multiplication formula, to something lower, using, say, Strasson's algorithm or a different matrix multiplication algorithm. But in general, when we're just trying to get like a sense of the runtimes, not like what is the best possible runtime, just getting a sense of the runtimes. People think of matrix multiplication as being cubic, and so it's simplest just to put into the cubed up here instead of into the 2 point something something something, which is harder to reason about. So for the oral exam, what are the sort of things that you have to know about this type of problem right here? The first thing is that, again, I am going to, when you come into my office, I will randomly select by rolling a dice which of the two algorithms you're going to have to explain to me, either the power method or the exponentially accelerated power method. And whichever one comes up, you will have to provide a 2 to 5 minute explanation that you should just have memorized about that particular method. And that explanation should include some sort of derivation of the runtime like this. It should also include like a basic understanding of the formulas that are involved here, what the formula is for doing the iteration here. And they're in some sense both the same formula, but again, because of that reparenthesization, there are different things that actually happen, and you'll have to be able to explain that to me. Again, like 2 to 5 minutes is not a long period of time, so you can't explain absolutely everything in that. You should explain the things that you think are the most interesting, the things that you think best demonstrate your knowledge. It's okay if you skip some levels of detail. And then I will ask follow-up questions if you skipped something, like maybe you skipped this whole derivation right here and just jumped to this runtime, I might ask, where does that n cubed come from? Or some sort of follow-up question like that. Another example of a follow-up question I might ask on this exponentially accelerated power method, EAPM, I might ask, why can we not store the Q over here as a sparse matrix and take advantage of sparse matrix multiplication? That's the sort of question that you should be able to answer. I'll actually write it out. I think it's written out below as one of the explicit questions, but I'll write it out here. Why can Q not be a sparse matrix and result in a faster runtime? But I will ask these sorts of questions as follow-up questions to try to probe exactly how much knowledge you have about the different techniques, how well you're able to reason about different things. My guess is that, and in the past when I've done this, vast majority of students come up to a spot where it is beyond your knowledge and you don't know what to say or you don't know the answer. And again, it's okay to make an educated guess. It's okay to say that you don't know the answer. And as long as you make reason through your educated guess well, then you will get lots and lots of points and very likely not miss any points. It is perfectly possible to get full credit on the exam and have not known the answer to many of my questions, as long as you're reasoning through things well. Oh my God. Good question. The question is, for the PageRank coding assignment, are you only supposed to do the power method and not the exponentially accelerated power method? And the answer is yes. And in fact, it is, if you try to implement the exponentially accelerated power method, the runtime for that method would be very, very large. Sometimes we call it like a galactic algorithm, because the runtime would be beyond the length of the observable universe, that it would take billions of years to run. And the reason that it would take so long to run is because of this n cubed value right here. That on the homework assignment, the value of n on homework, we go blue here for the color, on homework, n is something like 10 to the 8th. I forget the exact number, but something on that order. So n cubed is something like 10 to the 24th. And this is just an absurdly large number about how long that matrix multiplication is going to take. And so the exponentially accelerated power method, despite its name, is actually significantly slower than the standard method for very, very large values of n. And you would have to use the standard power method with sparse matrices on the homework assignments. Good question. Sort of type of reasoning about things that could come up on the oral exam. And I would expect you to be able to reason through like, oh, the exponentially accelerated power method is going to be really slow when n is very large because of this cubic thing right here. But the standard power method will be really fast. And so we don't, we would prefer to use the standard power method when n is large. And again, the sample questions down here are trying to get at those types of things. If you can answer all the questions on the notes packet comfortably, then you'll do well on the oral exam. Any other questions about PageRank-ish things, exam things? Go back up to this.
So it's squiggle squared to the k.
Squiggle here, pronounced alpha to the 2 to the k. Yes. Alpha to the 2 to the k. Yes.
Does the homework assignment change from, I accidentally copied it from 2 years ago for the GitHub? Has the assignment changed since then?
Let's see. So two-part question here. I'm going to first answer in general and then answer in specific. The general answer is that on the GitHub repository, there are a lot of folders marked future that you're welcome to look at, but you shouldn't like copy stuff out of because things in the future could change. And once it's like out of the future folder and I put it into the regular folder and talk about it in class, then is a safe time to access it. It won't change. In this particular case, if you went into one of these future folders and got the PageRank file, for this year, I updated some of the instructions just to clarify things, points where people had trouble in the past. I think I added some more comments in the code maybe, but the code itself and the details of what you're actually supposed to do, the instructions for submission did not change at all. Okay, then for the remainder of today, we're going to start talking about this new textbook, Learning from Data. And the notes packet for that, for our first discussion, looks like this. I have a big, long wall of text up here, which would be good for you to read. It's mostly about strategies for how to succeed in this portion of the course. But some highlights are that the textbook has 5 chapters. We will cover all 5 of those chapters, and you will be expected to know everything in the textbook. The textbook itself is written by somebody from Caltech. I like to, again, whenever I'm reading something, just see who the people are that are the authors. So this is one of the authors. He's the main author. These other 2 guys, him and him, are sort of side authors. Both of these 2 people were PhD students under this main author here. So this was really like his project, and the other 2 guys were just working with him. This particular textbook, the reason that I chose it is because it is the only textbook that covers the actual math behind machine learning that is suitable or targeted for an undergraduate audience. So the vast majority of undergraduate machine learning courses that are designed to cover the mathematics of machine learning use this textbook. Again, we're not going to be talking about implementing algorithms, the machine learning algorithms in this class. We're not talking about the implementations. We're focusing on the math behind what the algorithms are doing, so we understand when to use one algorithm versus another algorithm. The non-undergraduate versions of this sort of stuff are extremely dense material, where the sort of average pace of reading is like 1 page an hour. This is a very fast, light reading of 5 pages per hour. That if you are going at 5 pages per hour, then you have a good like average pace of reading here. If you would like to see some different lecture videos on some of the content from the textbook, the author does have his own lecture videos here. Some of the differences between what I do and what he does are that he focuses more on proofs of theorems, more on implementation details, and I focus more on understanding when and why a theorem applies, what it means, what's its implication for us as practitioners, and how to select which algorithms to use. Again, the focus of this course, the reason we're talking about the things we're talking about in this course is because when you go on, if you're a data science major, to the data science capstone, these are the techniques, the things that you'll have to be thinking about, the theorems that you'll be applying as you're deciding what algorithm to use. But in the capstone course, for example, you will never be implementing your own version of, say, decision trees or the perceptron or neural networks. You will never be implementing those from scratch because lots of other people have done that, and we will just use their code. Instead, we will be deciding when to use which algorithm. And that's what our focus is going to be on. Last sort of note here is that like the reason we covered the PageRank stuff before this is because this textbook dives right into, assuming that you have a lot of linear algebra background, doesn't necessarily require the PageRank stuff, but it does require all the understanding of like computational linear algebra, these iterative algorithms, and eigenvectors, ranks, things like that, properties of matrices. And so the studying that you're doing right now for that first midterm exam definitely will pay off also for this, this section of the course. Okay, now into some technical stuff. And maybe too, one thing I'll point out is that my notes here are designed to follow very closely the overall structure of the textbook. So if as we're going through the notes, there's something that you feel like you don't fully understand as much as you would like to, then I've highlighted where, like which figures or which sections in the textbook are the references for these different problems. My hope, again, is that you will have, by next week, read through this first chapter here, that will help you as we're going on through these notes sequences. Yeah, these are the references right here where they correspond to different things in the textbook. Okay, all that said, let's actually get into this problem set up here. The first example that the book uses is the example very fitting for, I think, CMC. I've actually done this exact problem with some students in their practicum courses, where you are a bank and you need an algorithm for determining whether to approve a credit loan or to not approve a credit loan. And I'm going to draw a big picture down here that's going to illustrate at a high level what the different notation and concepts are that we will be using in this portion of the course. So the first thing, and this again is coming from figure 1.2 in section 1.1. This is going to be a figure that the textbook will continuously add to over the first chapter here, modifying things. The version of the figure that we're going to draw today is not something that you'll have to memorize, but the final version of this figure is something that you'll have to memorize. Okay. So what are we actually doing? Well, the figure starts with there's some magical function from x into y. And what this magical function is that it's like it's some function that we don't know, that we can't compute exactly. And in this case, this is like a magical function that tells us exactly who is the best possible person to give credit to. Tells us exactly who to give credit to. And by credit here, I mean like extend a loan, whether to approve a loan to somebody. This is our motivation here, that we want to know who we should extend some loan to. We could, in the past, say like in the 1800s, banks would just have this idea in their head of like who are creditworthy people, like nobles, people with a lot of property. But modern banks all use data to determine this, that we have realized that humans are very bad at trying to write these functions by ourselves, and you get much better functions learning things from data. So that's what this F thing is. This X here, these are it's sometimes called the input space. These are what the examples look like. So this X here would be like some sort of description of a person. Description of a person. And our framework right now is general enough that this description could be like some piece of text. It can be a vector with various features inside of it. It's just some description that we're formalizing somehow. And this Y value is the thing that we're interested in of should we actually give credit or not. And eventually we will be making this Y value either +1 or -1, where +1 is basically the same as yes, we can give them credit, and -1 is no, we should not give them credit. This F function over here, let's see. So yeah, the X, I specifically said that's called the input space. This Y, sometimes called the output space. This F function goes by many names. The textbook uses many different names. Some people call it the God function because it's the sort of thing that only God could know. That it's not like actually available to us as mere mortals. Some people call it the perfect function, or the true function, or the ground truth. All of those names being fully synonymous with each other. So this thing here in red, this is the thing that we want, but it's the thing that we don't know how to implement, we don't have direct access to. And so this whole idea of learning from data is how are we going to find some sort of approximation to this F. The first thing that we do in this framework for this textbook is that we come up with some examples. And the notation here that the textbook uses is that these examples are pairs of little x comma little y. Little x sub 1 comma little y sub 1, and so on up to little x sub capital N comma little y sub capital N. Each one of these xy pairs, so one x comma y pair, is just called a data point. And the large value N over here, capital N, is the total number of data points. The total number of data points. This setup that we have at this point is an example of a supervised problem. Sometimes called a supervised learning problem, because we have this x as our input to our function, and we also have the y, which is the output to our function. We are making the assumption which may or may not be true. And most likely this assumption will not be true. We'll be talking in the next couple classes how to relax this assumption. But we'll be making the assumption that for each y sub I, that is equal to f of x sub I. So again, this f is not something that we have access to. It is something that the universe has defined for us some way, that there is some immutable property of what makes somebody creditworthy versus not creditworthy. And that is what this f function is. And this y value over here is applying that f function to the x sub I. So in this particular case, these y values, these y values in our examples, so the little y sub I is going to be whether somebody actually paid back their loan or not. Is whether someone, and in particular that x sub I person, actually paid back the loan. And at this point, there's a lot of, a lot of these words have probably you've seen before in different contexts. There's going to be very formal definitions of all of these words that will be very important, and it'll be very important that you keep track of those formal definitions throughout this class. Again, this figure that we're drawing right now is going to have a more complicated version later on in 1 or 2 lectures, and that more complicated version will have all sorts of terms in it, and you'll be responsible for memorizing all of those definitions. The reason why I say that one will be more complicated is because this assumption right here will be relaxed into something that is less strict. This is a very strict assumption right now, a very unrealistic assumption, because it's unrealistic that like the universe can know in advance whether somebody is going to pay back their credit or not, no matter how much information you provide, no matter like what the contents of this xi value is. Some future circumstances unrelated to that person could determine whether they pay back the loan or not. So maybe as an example, like if I applied for a house loan right now, then like I have a stable job, I have a good income, I'm creditworthy, but maybe the United States like goes to war with Mexico tomorrow and the economy crashes and now nobody can pay back loans. And so like this sort of assumption right here is assuming things like that can't happen. So this is a very strict assumption. And again, we'll be talking about ways to relax that, and that's going to be the important part of the next couple lectures. If this assumption is not fully making sense at this point, why we have it or why it's a strict assumption, this part over here will get clarified in future lectures. Hopefully the parts up above, these parts are so far clicking though. I'm gonna, it's a good spot to pause for questions. Hamaka. The question is, are the yi's in the form of 1 or -1? And the answer is yes. That when I said this, sometimes, so the textbook here, the particular font of the y they use is called a script y or a math-cal y. I draw that with a little circle up here. Any sets in the textbook have this circle scripty font over here. This set y, I'll be a little bit more formal over here with what I wrote out in words. I will use orange in this part over here. The set y is equal to, in this case, +1 or -1. And every little y sub I is contained in the script y like this. So every y sub I is going to be contained in +1 or -1. This x, I haven't given any examples or I haven't defined what this set of possible input space things looks like. So I can't say particularly what x is equal to, but I can say that every x sub I is contained in script x like that. This little e-ish thing being the containment operator, that the thing on the left is an element of the set on the right. Good question. Any other questions so far? lot of jumbled space over here. Yes.
Is there a reason why we're using positive one, negative one, instead of 1, 0?
Yeah, that's a good question. Is there a reason why we're using +1 and -1 versus 1 and 0? The answer is that it happens to be the case that will make certain math things in a few pages a little bit more convenient. But you could equivalently make this be a 0 and a 1, or a 0 and a -1, or an A and a B, or all sorts of other choices that end up being mathematically equivalent. And lots of other textbooks or papers, it's convenient for them to use slightly different notation. So for us, it'll be convenient, at least for now, to be +1 and -1, but that's not like a hard and fast rule about what y has to be. Good questions. Okay, the next part of this is that this is all fed into an algorithm, which they use as a big circle with a funny looking A as their name for their algorithm. And the algorithm is going to output some function g, which will be approximately equal to f. Some function g, which is approximately equal to f. G right here is the output of the algorithm A. And the main thing that we're going to be studying in this next part of the course with this textbook is, like, how can we guarantee that G is either equal to A or approximately equal to A? Like, under what conditions is G actually approximately equal to F? And the most important of these conditions is going to be, like, how much data do we actually need? How big should N be? This capital N, again, being the total number of data points that we have. Most undergraduate textbooks on machine learning do not even attempt to answer these questions, but they're somehow the most fundamental, important questions of machine learning. And so the reason why we're using this textbook is because it does answer these questions. Another thing that most other textbooks do not do is that there is one other piece over here called the hypothesis class. And this is also going to be an input into our algorithm. It's always denoted as this script H right here. And our algorithm is always going to have two inputs into it. One is going to be this training data up here. So this is the thing that if you've done any sort of machine learning stuff before, this is the thing that you've been thinking about as the input to your algorithm. But the other thing, which is sort of very implicit in machine learning from data, data mining, is implicit is what is your hypothesis class that you're actually using for your algorithm. And this hypothesis class, first of all, anytime you see the word class, if you see the word class, that just means the same thing as set. So this is a set of hypotheses, or a class of hypotheses. And our G function, the thing that is our output of the A algorithm, G is going to be a subset of H. And our algorithm is going to return some element of this hypothesis class. G is sometimes called a hypothesis. So our algorithm is going to return some hypothesis in this hypothesis class. And we're going to be studying the properties not only of individual algorithms, but also this hypothesis class. So we will study vast majority of the things that we'll be thinking about are properties of these hypotheses classes. We will study H and its properties. I'll say, and what makes a good H? What makes a good versus bad hypothesis. So again, big picture idea, what's going on here is that we have some, all of the problems, whether it's selecting whether somebody should be given credit or not, whether it's predicting what letter is inside of a picture, whether it's predicting anything, they can follow this basic framework where there's this some like invisible to us function that is the true function, the ground truth of our problem. And we have some samples, X and Y, where the Y values are applying the function, this ground truth function, to the X values, and they give us some result as the Yi. We apply some algorithm to that to find out this G function, which is approximately F, and we're going to study under what conditions is our G function, the thing that is the output of our algorithm, under what conditions is it good. Ambika. Yeah, it's a complicated diagram here, complicated page, lot going on. Again, though reproduced from figure 1.2 in the textbook. And so if there's something in here that you didn't quite fully catch about one of these things, think there might be some subtleties that you didn't get, that's the figure to make sure that you reference and understand, and the corresponding text in section 1.1.1 will help you out there. And again, at this point, you do not have to memorize this. We'll have an even more complicated version of this in one or two lectures, and that will be one that you'll have to memorize with all of these different definitions of things. At this point, this is just like our stepping stone to get us there. Yes, Samika again.
Is that a boundary or is this the algorithm?
The algorithm outputs an element of the set. The G over here is an individual function. H is a set of functions. G is one function.
Okay.
That answer? Yeah. Okay. One of the things that makes all math hard is there's some sort of like alternation between lots of abstract definitions and then like why do we have those abstract definitions? And then going into concrete examples about why the definitions are the way they are. But in some sense, you can't actually do the examples without the definitions, and you can't do the definitions or understand the definitions without the examples. So if there are things that are here are not fully making sense, that's okay. We'll make things a little bit concrete here with this thing called the perceptron hypothesis class in this next problem. And the textbook, once it starts talking about this perceptron hypothesis class, does not necessarily refer back to the this problem, this idea of predicting who is creditworthy or not, but I'll try to make the connections a little bit more explicitly here than is in the textbook. So the first thing here is define the perceptron hypothesis class. And one of the things that this book does is that it starts with, at least in this first chapter, it starts with definitions that are relatively less intimidating using non-linear algebra stuff. But then it will provide more potentially intimidating but more succinct definitions later on. So this hypothesis class looks something like this. This is their first definition of the hypothesis class, where the sine function right here, the sine function, say of any input A will be equal to +1 if A is greater than 0, or -1 if A is less than 0. And then these W sub i's up here, these W sub i's are called the weights of a particular feature I, weights of feature I. The X sub I, this is the value of feature I, or just feature I. So value of feature I. And this B right here called the bias term. This bias term is totally unrelated to bias about yeah, I don't know. Since we're talking about credit right now, there are algorithms or there are laws that say that algorithms cannot, for example, discriminate based on gender or race or religion or many other protected attributes like that. This bias term has nothing to do with that kind of bias. It's just called a bias because we're because of historical reasons. And so this is what an example of the hypothesis class for the perceptron hypothesis class looks like. This is one way of writing it out. Some assumptions here about the perceptron hypothesis class that are not fully explicitly stated in the textbook. It's just sort of assumed that you can understand that this assumption is being made. But some assumptions are that the X set, the input set, comes from or is equal to, I'll make that an equal sign right here, X equals R to the D D right here being the number of features. So we have one dimension per feature. And then the Y here, again, is the same as it was before, +1, comma, -1, like that. This thing, X equals R to the D, not something that's clearly laid out maybe as well as it could be. But the perceptron hypothesis is only valid for input data that is a vector-ish form, not things like raw text. Any questions so far about any of this notation? Lots of new things that I'm just sort of barfing out at you all at once here. But any questions about this? Yes?
Just to clarify, is it ever possible for A equals 0, or is that not possible either?
This is a great question. So the question here is what happens if we pass in A equals 0, and like over here in my cases, I have an A greater than 0 and an A less than 0. It turns out that that doesn't matter. You can arbitrarily say one of these is greater than or equal, or the other one is less than or equal, and it won't change any of the things that we'll talk about. So the textbook explicitly says they try to be ambiguous about here about what to do in the case of 0 because it doesn't matter, and you can choose whichever thing you want. But that's a good question. So we can make that a little bit more concrete. Just arbitrarily, we'll say +1 gets the 0 case. Good question. Any other questions so far? Okay. So again, the textbook, trying to have a gentle introduction to these things, will write things out in different ways with increasing levels of abstraction. So this first figure that we talked about above, we're going to see more complicated versions of that. And similarly, this hypothesis class right here, actually just like several paragraphs after each other, more complicated versions of this hypothesis class are introduced. So let's see, I'm running out of space a little bit, so I will, I'll write that into this 2 section right here. It turns out there are 3 versions of this hypothesis class that are all mathematically equivalent, and the textbook uses them interchangeably. So I'll write it out all 3 of those versions here. And the stuff that I'm doing currently below 2 here should be up here. So another version is h of x equals the sign of W transpose X, just observing that this whole expression right here is a inner product between a W and an X vector that are specially constructed. So this is a more succinct version of the same formula up above. Another version of this, one thing that is you may have noticed we have not talked about is this like script H, the actual hypothesis class itself. Sometimes you will see this as written where H equals the set of X, funny arrow, sign into W transpose X like this, colon, X colon W contained in R to the D. All of these notations are the exact same thing. So this is number 3 here. There's number 2 right here and number 1 above. These are all semantically the exact same thing, but you'll see the textbook write the same thing in these 3 different forms, depending on what they think is the most convenient. This notation down here is likely to be the most new and weirdish to everybody, so I'm going to break it down one step at a time here. This little funny arrow thing, this is called function application. Application, and it means there's an I don't want to say that programmers invented this, but programmers sort of popularized it in mathematics with the idea of in Python it's called a lambda function, because the keyword for using it in Python is lambda. More generally, it's called an anonymous function. Anonymous function, and it's anonymous because it doesn't have a name. This function up here, this function has a name. Its name is h. This function down here does not have a name. We just know what it does. We don't have a name for it though. This x thing right here corresponds to this x up here. That's the input to the function. And then this whole thing right here, you notice that it's exactly the same as that whole thing right here. That's the output of the function. The w over here, anytime you have this whole like notation where you have curly braces on both sides, this is often called set builder notation. Set builder notation. And anytime you're using set builder notation, the stuff after the colon over here, these are all of the variables used on the left-hand side in this output section over here, but that are not defined as inputs to the function. So all variables that are not inputs. In programming terms, this whole construction is related to, say in Python, is related to a list comprehension. So if this notation is not making sense to you, if you look up list comprehensions in Python, then list comprehension, set builder notation equals list comprehension, then that should hopefully help this notation making sense. Any questions about the notation? Any of those notation things there? Yes.
These 2 are saying the same thing.
Yes, so the 3 different formulas that I have up here all define the exact same hypothesis class, which is called the perceptron hypothesis class, and they all are 100% equivalent to each other. The authors of the textbook and of everything in general will use those 3 different formulas, whether using breaking out the linear algebra stuff so that it's no vectors and matrices, combining things together to use matrices or vectors, or using the set builder notation. People will use all those things interchangeably, and they all mean the exact same thing. Yeah.
W, I think you said all variables that are not, or is it are or not?
All variables that are, you're right. So I missed the word not right here. All variables that are not inputs need to be defined over here to the right of the colon. So here we have x as an input to this function. So there's an x over here, and the w is not an input to a function. In order for us to know like where w comes from, in the set builder notation, it has to be specified to the right of this colon over here. In these other notations, there's no specific way to specify like where w comes from, what it means, and so the surrounding text has to clarify that particular thing. This set builder notation version is the most compact in terms of providing all the information that's needed to provide this to define this hypothesis class, and so this is the most common thing that practitioners will talk about. The textbook starts with the version 1 and 2 in order to make it a little bit less intimidating before getting to part 3. Yes?
Are we saying that list comprehension is
The things on the left over here, independent of the things on the right, that a list comprehension is the Python equivalent of set builder notation in math. An anonymous function or a lambda function is the Python equivalent of this function application symbol right here. Let's see. I want to do one last thing today, and that's actually do this problem 2 right here. It doesn't take a lot of space, so there's space, at least on my notes right here, to do it down here. You know, that's the anytime you have one of these hypothesis classes, we're going to be seeing probably like 20-ish different of these hypothesis classes throughout the course. It's good to have some sort of concrete visualization of what these terms do, what these classes look like. And so in two-dimensional space, if I draw my axes like this, the x values will define where a data point is. Maybe do it like this. X sub I is where the data point is. And then the y sub I being the label is whether it's positive or negative. Whether it is plus or minus. It's over here on this little figure. I'm going to draw an example of a data set where we have some pluses like this. So the x sub i's, again, are determining where these pluses are located. The y sub i's is determining that they are, in fact, pluses. And some minuses over here. And the hypothesis class, perceptron hypothesis class, the intuition behind it is it's the class of all straight lines that decides between positives and negatives. So this would be an example of a good element of that hypothesis class, where over here things are labeled plus and over here things are labeled minus. This would be a good G in H because it's correctly putting all the pluses on one side and all the minuses on another side. But an example of a bad G sub H would be, say, like this right here, where we put the pluses on this side and the minuses on this side. This would be a bad, spell that better, bad G right here, because now there's a lot of things that our G function here is labeling them as they should be positive over here, and it matches these positive ones, but it doesn't match these negative ones over here. It doesn't agree with it. This is a bad G, not what we want, but it is still contained in the hypothesis class. This G is still contained in H, and so our algorithm somehow has to determine that we want this orange one up here that actually separates the pluses and the minuses, and not this gray one over here, which is bad and doesn't separate the pluses and the minuses. So we'll talk about what that algorithm looks like next time. Question? So the question is describe, I think, basically go over the meaning, the semantics of this graph again. So here when I say the xi is where the data point is, this is like a coordinate pair. So this is a coordinate pair. I've drawn this as like an XY axis, where this, like, you'd normally think about this as like being the X right here and the Y up here, but that's not the way to think about these graphs. This is like the first position of X right here, and this is the second position of X over here. And so this value right here, this particular data point, that might have a, call this data point A. A's coordinate, or x sub A, would be equal to, say, 1, 1, because it's in this 1, 1 location right here. But this location right here of B, x sub B, would be equal to, say, -1, -1, because it's located in -1, -1. This location right here, C, x sub C, x sub c would be located at -1, 1. And you can see that the values of the x's over here are independent, not related to the actual labels themselves. The true function that we don't know what the structure of this true function is. We just know that somehow y sub a, its definition is that it is this true function f applied to the data point x sub a, applied to this coordinate pair right here. And this function is, whatever it happens to be, which we don't know what it looks like, we know nothing about it, is going to just give us a value of either +1 or -1. And again, the only thing we know about this function is that on this particular data point, it happened to give us the value of +1. Similarly, for on y sub b, it happened to give us the value of -1 over here. We don't know how it did that. We don't know what it did. We just know that that's what it happened to give us. If you're trying to think about like intuition about like how this works in the real world, our model is not yet robust enough to talk about the real world, because the real world has things like noise that you have to account for. It has things like non-determinism, where even if there's no noise, you just don't know, you can't predict the future. And so this is not a realistic model at this point. This is just a model that we have that we will make more realistic in the future. We're pretty much out of time for today. So again, if you have more questions about this, it's totally okay that I just barfed out like 30 different terms and definitions of things, trying to get you some sense of where we're going in the future. Strongly recommend that you read through that first chapter though, which will hopefully clear some of the edges, rough edges around for this. Next time we will do more examples of this to help clarify a lot of these definitions for you. But if you do have more questions about any of these specific things, happy to stick it around and get those answered right now.